than 0. All right, so now what I'm going to do is I'm actually going to FOIL out the 2k plus 4 times another 2k plus 4. Is 2k plus 4 times another 2k plus 4, is that 4k squared plus 16? No, it's going to be 4k squared plus 16k plus 16 minus 4 times 4 is 16. 16 times 16 is 256. So now we're going to combine our like terms here. So now we have 4k squared plus 16k minus 240. Before I go any further, I know a lot of you are going to say factor, and that's not wrong. But before we factor, we have to look at this. This is not an equation. This is an inequality, but not just any kind of inequality. This is a quadratic inequality. And if you guys remember in the beginning of the year, when I first initially taught this, I said it's going to keep finding its way into random chapters. So don't forget it. So when you have a quadratic inequality, beyond factoring, what process are we doing? We're going to test the regions. Exactly. We have to test the regions. But before we test the regions, to find our reference numbers, we have to factor. So I'm going to pull out a GCF of 4. K squared plus 16k, plus 4k minus 60 is less than 0. I'm going to leave that 4 there, and I'm going to factor. So I'm going to leave that 4 as the GCF. So we're going to have a k plus 10 and a k minus 6 is less than 0. So here we're not solving. We're getting our reference numbers. So our first reference number is -10, and our second reference number is +6. And when we test the regions, do we want the product to be positive or negative, and how do you know, Stephen? Negative is less than 0. Good. We want the product to be negative because it's saying it's less than 0. Now, this GCF of a +4, is this going to change my outcome of the products having a +4 GCF? No. Having a negative, though, would that change the outcome of the product? Yeah. So oh, thank you. This should be K. So now we're going to test the regions. You're going to go to your smaller number, which is -10, and we're going to test smaller than our smallest number. And then we're going to test in between our two numbers, and then test greater than our larger number. Now, this GCF doesn't affect us, but we said if it was a negative, it would affect us. So just to get in the habit, I'm just going to put a positive, positive, positive for that GCF in each of these columns. Again, we know that positive won't affect us, but if it were negative, it would affect us. So that's why I'm doing this. And now I'm going to test a number less than 10, no, less than -10. What number is less than -10? -11. So I'm going to test now -11 plus 10. All I care about is positive or negative. Do we all agree -11 plus 10 is a negative? And then -11 minus 6 is another negative. So if I have one positive and two negatives, what does that make? Positive. Do we want the product to be a positive? No, we want the product to be negative. So the first column X's out. What else X's out? The third column. We still have to check the middle column. So now I'm going to check a number between -10 and 6. We're going to choose 0. 0 plus 10 is positive. 0 minus 6 is negative. Two positives and a negative is a negative. This is what we want. So our solution set is going to be K such that -10 is less than K, which is less than 6. When do we test the regions? When do we test the regions? Just V, no? Change your mind, yes. Not just any inequality. So if I had like K plus 4 is less than 0, I wouldn't test the regions for that. So what kind of inequality? One where you have to do what? Yeah. So it's when we have a quadratic inequality. When you have an inequality that you need to factor, that's the only time we test the regions. Do we test it for every inequality? No. Do we test it for a quadratic equation? No. We only test it when we have an inequality that needs to be factored. That's it. All right, new lesson. Yes.
Can you go back to the step where it was four x k squared plus 16 minus 256? Could you not have just added 256 on both sides and saw that that was a square root?
You could. So you could have absolutely done this. But no matter what, so if you, it was easier knowing, recognizing that this was a quadratic this way. So if you left it at this, you're saying move the 256 over. So you would still need to know this is a quadratic inequality. How would you now know that it's a quadratic inequality? Because this is square. So you still have to test the regions, but you can solve square root method to get the two reference numbers. Do you see what I'm saying? Do you want me to keep going this way to show you?
Yeah.
Okay, so if you were to do this, you would have square rooted both sides to solve. So then you would have 2k plus 4 is less than plus or minus 16. And then you would have 2k plus 4 is less than positive 16. 2k plus 4 is less than negative 16. And you'd get your two reference numbers. So your two reference numbers would be 6 and negative 10. And then you would have to test the regions. So you still had to recognize it as a quadratic inequality and you still had to test the regions, where this way it's a lot harder to see that, but it's still the same. Okay. Solving radical equations is what we're doing today. Okay, so our first step when solving radical, or I should say, or exponential. So solving radical or / exponential equations. Oops. Okay, so step number 1, you're going to, if possible, sometimes it's not possible. So if possible, get the radical by itself. Step number 2, we're going to use the index to get rid of the radical. And lastly, you're going to solve for the given variable and check for extraneous solutions. Okay. So let's talk about the checking for extraneous solutions. The last time we were checking for extraneous solutions is when we had variables in the denominators. And we had said we had to plug back in to make sure that none of our values made the denominator 0, because when the denominator was 0, that would be undefined. Basically, it didn't fit in our domain. It's going to be the same thing with this. We have to check to make sure that the answers fit within the domain, that the statements are still true. So after we get our answer for X or Y or Z or W, whatever variable we're solving for, we're going to plug back in to make sure that the answer holds true. All right, let's just jump right into this. So let's say I have the cubed root of 6x plus 10 is equal to -2. We're going to solve for x. Well, right now I have a radical. I have the cubed root. My first step was to make sure that radical, or the expression that's raised to the exponential, is by itself. Is it by itself? Yes. So I'm going to write this as an exponential. This is 6x plus 10 raised to the 1/3 power. Do we agree? So now I have to think. I'm going to raise a power to a power. What would I need to raise the 1/3 to get it to be 1? Stephen? To 3. We have to raise it to the power of 3 on both sides. So when we raise it to a power of 3, the 3's cancel. So now I'm left with 6x plus 10 is equal to -2 times -2 times -2, which is a -8. We then solve for x, and we're going to get 6x is equal to 6x is equal to -18, so x will equal -3. All right, the check. To check this, you just need to plug back in. So we're going to have the cubed root of 6 times -3 plus 10. So we're going to have the cubed root of -18 plus 10. Oh, sorry, has to equal -2. Is the cubed root of -8 equal to -2? Is that true? Yeah, so our check works, our answer is good. Yes. Then it's no solution. Okay, next one. We have 3 plus the square root of 3x plus 1 is equal to x. What should I do? Do what? Good. We want to get the radical all by itself. So I need to move this 3 over. So I'm going to subtract 3 on both sides. I'm going to rewrite my problem. So I'm subtracting the 3 here, and I'm subtracting the 3 here. This cancels. So now we have the square root of 3x plus 1 is equal to x minus 3. Do we agree the square root of 3x plus 1 is the same as saying 3x plus 1 raised to the half power? Okay, so what am I going to raise the half power to get it to cancel to 1? Stephen? 2. So we raise both sides to the second power. The 2's will cancel. So now I have 3x plus 1 is equal to x minus 3 quantity squared. What should I do now? Any ideas? Still need to solve for x. Justin?
Foil.
Good. We have to FOIL the right side. So we're going to have 3x plus 1. Is this going to be x squared minus 9? No, it's going to be x squared minus 6x plus 9, right? Do we all agree we're going to have to factor here? Do I have to test the regions when I factor here? No, because it's not an inequality. I just need to set it equal to 0, and then I'll be able to factor. So now we have x squared minus 9x plus 8 is equal to 0. So we're going to have an x minus 8 and x minus 1 equals 0. We will get x equals 8 and x will equal 1. It is okay to have two answers, but do we have to check? We still have to check. So I'm going to check, and to check, you're going to go back to the original equation, which was 3 plus the square root of 3x plus 1 equals x. So we're going to have 3 plus the square root of 3 times 8 plus 1 equals 8. Well, 3 times 8 is 24. 24 plus 1 is 25. What's the square root of 25? 5. Is 5 plus 3 8? Yes, so that check works. I'm not done. What do I need to check now? The 1. So we're going to check 3 plus the square root of 3 times 1 plus 1 equals 1. 3 times 1 is 3 plus 1 is 4. What's the square root of 4? 2. Is 2 plus 3 1? No. So this rejects. So we're going to reject the 1 and only have x is equal to 8. Okay. All right, here we have the cubed root of 2y raised to the negative first power equals negative 4. I'm going to change this into exponential. Do we agree this is 2y to the negative first raised to the 1/3? All right, so for a couple of reasons, this is not a power to a power. I can't make this to the negative 1/3 because is this 2 raised to the negative 1? No. And even when we have multiple exponents and I'm raising them to each other, I sort of want to treat them separately. It will help avoid any minor mistakes that can be made. So we're going to deal with each one by itself. So the first one is the positive 1/3. What would I raise the positive 1/3 to? Not Stephen, because he's told me the last 2 times to get it to cancel to 1. Yeah, 3. So I'm going to raise to the 3rd power here and the 3rd power here. So now here the 3's cancel. So now I have 2y to the negative first power equals negative 4 times negative 4 times negative 4, which is a negative 64. Can I divide by 2 on both sides? Yeah. Is that 2 being raised to the negative first power? No. So I'm going to divide by 2 on both sides. So now I have y to the negative first power equals negative 32. What can I raise the negative first power to get it to be 1 to a power of 1? Say it one more time. Negative first power. Negative times a negative is a positive, so that's how we get y to the first power. And we end up with negative 32 raised to the negative first power. Well, to fix that negative, because we can't leave a negative exponent, wouldn't it just be negative 1 over 32? All right, next one. I will tell you the check works out. Check does work. So this is x to the negative second raised to the 1/3 equals 9. Now, in like 95% of the time, if you were to multiply these power to a power and then just sort of take care of it all in one step, it would work out. But then there's certain scenarios where if you multiply these power to a power, you end up losing something important. And I think it might show up in the homework, actually. I'm not positive though. So I like to treat them separately, meaning get rid of one exponent at a time. So first I need to get rid of the outer one. So how do I get rid of that power of 1/3? Get rid of that power of 1/3. Ilya, we raise it to the third power. So I'm going to raise this to the third power, which means I need to raise 9 to the third power. So now we're going to have x to the negative second power equals 9 to the third power, which is 9 times 9 times 9, which is 729. Okay, so now I'm left with x to the negative second power. I'm going to keep working with exponential. What would I have to raise and to x to the negative second by? What power would I have to raise it to for it to cancel to 1? Negative a half. And please don't go ahead of me here. That denominator is 2. What does that mean in radical form if that denominator is 2? It is a square root. And when we're solving for x and we have to solve by taking the square root of both sides, what do we have to account for? So like if I had x squared equals 16, when I'm solving, what do I have to say? Plus or minus. This is going to be, if there's a mistake that you make on the test, this is going to be the mistake. You're going to forget the plus or minus. Anytime the power that we are raising it up to, not the original, the power that we're raising it up to cancel out, anytime our denominator is even, we have to do plus or minus. For the purpose of this class, I will only have an even denominator of 2. But next year in pre-calc, you might see 4, right? You might see a different denominator. And at that point, that teacher will remind you. But anytime you have that even denominator, you would have to put plus or minus. For the purpose of this class, what's the even denominator I'm going to give? 2, exactly. So now which is the equivalent of a fractional exponent with a denominator of 2 is the equivalent of taking the square root, right? So now we're going to have x equals plus or minus. Now for me to take care of this negative, don't I just have to make it into a fraction? 1 over 729 raised to the half power. Everybody okay with what I did there? And raising to the half power, we said, is the same as taking the square root. So this is x is equal to plus or minus the square root of 1 over the square root of 729. Believe it or not, 729 is in fact a perfect square, which is 27. I will not give you a perfect square that big on the test. Okay, so the moral of the story here for this problem, anytime we raise to a fractional exponent that we're coming up with, that we're writing down, and that fractional exponent has a denominator of 2 for this class, but for future classes has what kind of denominator? Even, right? An even number. You want to account for plus or minus. You want to account for plus or minus. For the purpose of this class, anytime I raise a fractional exponent to another fractional exponent, the one we're coming up with has a denominator of 2, we have to account for plus or minus. All right, you guys try this one. Actually, we'll do it together. It's a little bit different. All right, is the radical by itself here? Yeah, the radical's by itself here because that whole quantity is raised to the 2/5 power. So radical's by itself. So now I need to think, what can I raise 2/5 by to get it to have an exponent of 1? Good, the reciprocal, 5/2. But what do we have to realize? 5/2 has a denominator of 2. So what do I have to account for? Plus or minus, you got it. Do you see how easy this is to overlook while you're taking a test? We don't want to, though, because now you're losing half your answer. We don't want to do that. So now these cancel. So I now have x minus 3 is equal to plus or minus 4 raised to the 5/2 power. I'm going to work here with the 4 raised to the 5/2 power. If you guys remember in the exponents unit, I was really encouraging we do something when we have a numerical base raised to a fractional exponent. Does anybody remember what I was highly encouraging we tried to do? Rehan?
4x2 squared.
Yeah, we want to change that base into some number raised to the same as the denominator. So the denominator is 2, so I want to make 4 into some number raised to the second power. This is a very easy fix for us. 2 to the second raised to the 5/2. Why do I encourage that? Because what does that do? Yep, it cancels out that denominator. It cancels out the radical essentially, right? So now we have x minus 3 is equal to plus or minus 32. 2 to the 5th power is 32. So now we're going to add that 3 over. So x will equal 3 plus or minus 32. I cannot tell you, every year there's at least like 3 or 4 kids that leave the answer like this. Why is this? And they do all this hard work and then leave it like this. Why is this not good? Yeah, we can add these. So you need x is equal to 3 plus 32, but we also need x is equal to 3 minus 32. So x is equal to 35 or x is equal to negative 29. I will tell you both answers check. I haven't decided yet if I'm going to make you check on the test or not. I know. I haven't decided. We'll see. All right, let's keep going. That's very extreme. You will lose your mind if you have to check. All right, course of action here. Can I just raise each term to the second power? Many people say yes. I can just raise everything to the second power to cancel out the radicals. How many people say no? How many people don't know? No, you have to know. You have to know. Why can't we? Everybody that said no is right. Why? Steven. Nope, that's not it. Because if I had x to the half times 4x to the negative half, I could. So why? What changes it here, Steven? The plus sign. Isn't it always the plus sign? It's always the plus sign. All right, we cannot do it. It's a binomial now. So I can't just raise each individual thing to the second power. I can't do that. So let's see what this is. This is x to the half plus, is the 4 raised to the negative half power or just the x? So I'm going to move just the x to the denominator. All right, now what I want to do, this is an equation. I don't want to deal with a fractional equation. So I'm going to eliminate the denominator. How would I eliminate the denominator here? Yep, we're going to take that common denominator or that only denominator of x to a half and multiply everything by it. So x to the half times x to the half is just x. These x's cancel, so I'm left with just plus 4 equals 5x to the half power. Okay, so now I want to solve this radical equation. To solve the radical equation, the first step was to get the radical by itself. Is that 5 part of the radical? Is this 5 part of the radical? No. For multiplication, we can leave it there. We don't have to get rid of it. If it were a plus or minus sign, I'd highly get rid of it because then when we square it, we'd have to FOIL, right? But here, because it's multiplication, I can leave it. If you want to get rid of it, we can. How many people want to get rid of it? Doesn't matter. It will work both ways. So we'll keep it. So do you agree to get rid of this half? I'd have to square it. How come I'm not doing plus minus? How come I'm just squaring and not doing plus minus? No, but I want to know how come, like, for this problem, I had to do plus minus here. See, I had to write plus minus. How come this time I don't have to write plus minus?
You're not taking something out of a root, you're just like, well, like you're not taking something out of a root, you're just multiplying it to your root.
We're not taking the square root, right? We're not taking the square root. So there was a square root there, but are we the ones taking the square root to solve? No, we're squaring it. We're not taking the square root. How would we take the square root if the denominator that we were writing was 2? Does that make sense? So we're squaring it. We're not solving by taking the square root. So now when we square this, be very careful here. 5 squared is 25. So we get 25x because that 5 is not raised to the half power. And on this side, I have to FOIL it out. So I get x squared plus 8x plus 16 equals 25x. Do we all agree I'm going to have to factor? So move that 25x over. X squared minus 17x plus 16 equals 0. And we get x minus 16, x minus 1. And we get x equals 16 or 1, and they both check. Okay, next one.
Ew. Like looking at my notes. No, they are. I don't know how to say that. You know, for instance. You're right.
Okay, so here, do we agree this is going to be t minus 4 squared raised to the 1/5 power equals 4? Okay, so now I know a power to a power we can multiply, and that would be 2/5. And in this specific scenario, it would work. But there is certain scenarios that very rarely happen where when you raise that initial power to a power, it loses your denominator somehow because it simplifies, and then we lose the plus or minus. So that's why I'm always saying, let's just be cautious and just get rid of one exponent at a time. So now when I want to get rid of the 1/5, what do I raise that to first? To the 5th power. So now I'm going to have that 5th and 1/5 cancels. So I have t minus 4 raised to the 2nd power equals 4 to the 5th power. I'm going to leave 4 to the 5th power right now. I'm not going to change it. Not yet. Now I'm going to raise that power t to the 4th power, t minus 4 raised to the 2nd power. What am I going to raise this to now? To the half power. And what do I have to be aware of? Good, because that denominator is 2, I need that plus minus here when I raise it to the half power. So now we have t minus 4 is equal to plus or minus. Do we agree this is 4 raised to the 5/2 power? What am I going to tell you to change that 4 into? Good, 2 squared. T minus 4 is equal to plus or minus 2 squared raised to the 5/2. That way we can cancel out the 2's. So now we have t minus 4 is equal to plus or minus 32. So we'll have two answers. T will equal to 36 or negative 28. Yes. Why does what happen? So if you have like t minus 4 to the second raised to the I'm trying to think I'm trying to find a number that will cancel. 5, let's do the 5/2. Oh, no, 2/5, sorry. Okay, so let's say we have that. So if we're doing this separately, well, I guess we would get the plus minus here. I can't think of the exact one, but something sometimes will happen. Oh, did I have one where it worked out like that? No, in number 4, it should have worked out because you would have gotten negative 2/3 and then you would have multiplied by 3/2. So then you still should have gotten the plus minus for that one. For number 4? So this one would work out if we did. So if you had negative 2 raised to the 1/3, that would be a negative 2/3 power, right? And then you'd multiply by the reciprocal, which is 3/2 or negative 3/2. So that should work. But there is, I'm trying to think of a scenario where when you raise the power to a power, it basically simplifies and cancels that denominator. So then you lose the half that you would initially have done. That's why. Did I answer your question or no? Okay. All right, guys, I think we should have, do we have time for one more or do we stop here? Okay, we can stop here. That's fine. But you have enough knowledge for your